Well, good morning, good afternoon, wherever you are. My name is Jonathan Wise. I'm the VP of Technology here at CESMII and the Chief Architect for this thing we call the Smart Manufacturing Innovation Platform. Today, I'm really excited to be able to share with you some of the work that we've been doing over the past 12 months with CESMII members and CESMII project teams. The team has put together a couple exciting demos that we think kind of illustrate how we can move the state-of-the-art forward and help make all US manufacturers smarter. But before we dive deep on the technical details, I wanted to spend a couple extra minutes on one of the slides from John's keynote earlier in the summit. This slide kind of covers the hidden costs of smart manufacturing implementations. And I really want to drill in on this area here, the long poles in the equation. Why are they so long, and how can we shorten them so that we can reduce time to value? And from a technology perspective, I think there are some contributing factors to each of these long poles. On the infrastructure and the networking side of things, the reality is that we have a lot of legacy technology. Now, we could kind of tune this presentation to a wide array of kind of positions in your smart manufacturing journey. You might be at the very beginning and you have no automation, no information systems. You might be somewhere in the middle where you have good working automation systems, but not the information that you want. And you might be at the far end of the spectrum where you have both automation and information systems and you're using those to make decisions. We're going to aim kind of in the middle of the bell curve here. And we're going to talk today about a scenario where you're a manufacturer that maybe has some automation in place, but you're not getting the information that you'd like. You're not automating any sort of decisions based on that information. You're mostly at the control part of your journey. So if you're starting with a control system, you have some infrastructure and you can leverage that infrastructure to get data flowing and turn that data into information. But doing so kind of introduces some additional risks and some additional considerations that can be daunting at the outset. The software tools that you might deploy against that infrastructure is often entangled in proprietary platform lock-ins. So the same folks who made the automation hardware have attempted to make information software, and there's sort of a connection between the two that's not easy to sever. So if you want to try something new, you really only have one choice to explore that. And sometimes it's not the most cost-effective or most agile choice. There's an array of risks as we connect our systems around cybersecurity. We've seen some of those in the news lately, and we shouldn't take them lightly. Anytime we connect equipment, we're changing our security posture. If we deploy new information systems in an environment where there's lots of skills around automation technology, but limited skills around information technology, we have some challenges there as well, whether it's staffing up or getting new capabilities within our team. These are considerations that kind of go into this long pole. And then there's the hard reality that a control system, particularly one that's 10 or 20 years old, was not designed with information systems in mind. It was designed for deterministic control, and those were the right decisions for control, but they're not necessarily the right decisions for an information system. So this is on the infrastructure and networking side. When we actually move out of just connecting to the data sources, assuming we have good data sources, we have a number of other considerations as well. The fact that a PLC as a data source is a labeled set of electrical inputs and outputs or logical evaluations from the PLC is a useful set of data, but it is not an information model. That the electrical I/O is not necessarily what you want for an information system, although it may contribute. So we're going to deploy different information applications. We're going to use that data plus maybe some additional data. And each of those different information tools is going to, by necessity, require you to map the data you have to the data it needs to deliver its value. And for each tool, this is a manual mapping exercise. And I don't want to skip over that. We're actually going to spend a couple minutes on it in a slide or two. But this manual mapping is an artifact, is a result of the evolution of technology in this space. The reality that the tags that we have in a PLC can't necessarily be turned into information that you use to make a decision is something that we have to deal with, that we have been dealing with for the past 10 or 20 years. If we can't fulfill the information model that application requires, if it needs data in order to help us make a decision and we don't have that data, we need to add it. We may need to add additional instrumentation, or maybe we'll experiment with newer technology like soft sensors using machine learning to try to estimate values that we can't gather. Or maybe we even have to revert to new human processes where we send somebody out with a clipboard to record some values so that we can fill in the gaps. These information software licenses themselves can be expensive. And actually, from CESMII's perspective, we think that's where the value should be. If there is a great software tool that can help you make better decisions, that's worth some money. But the challenge of implementing that license, kind of everything to the left of that blue value creation there, comes along with the software license and can make the whole bill of materials kind of daunting. And it can lead to, pilot purgatory, where you've deployed it once, it seemed to work, but you're not quite sure how you're going to scale or reproduce it, or if you have to multiply those costs across every line or site where you want to repeat that solution. Because if you do, you invariably end up with long-term kind of maintenance and staffing considerations to go along with software, the servers that run the software, the operating system that runs on the server, all of which needs care and maintenance to keep healthy over the long term. So these are some of the factors that kind of create these long poles. And for our discussion today, what I wanted to do is sort of explore them in the context of an example operation. So this is a simple batch process that we're going to talk about today. And as we were sort of building this out, we wanted to think about these batch tanks in relationship with one another. So I have one batch tank that fills into another batch tank. Maybe one is storing material and another is used to mix material. Whatever it is, these batch tanks work in relationship with each other. So understanding the data in an individual tank is important, and then understanding how the data from one process unit impacts the data from another process unit can contain insights, and that's what we really want to get to. So if you've never seen a batch tank before, they're very common equipment. Odds are lots of manufacturing operations have one doing something or storing something. They're usually part of a larger system, right? These are built by a variety of OEMs for a wide range of industries, and they're often equipped with basic instrumentation, and sometimes they are connected to a PLC. So that instrumentation has representation in the electrical I/O in the backplane of the PLC, which has a tag. So they can be a data source. What's interesting about a batch tank is that because they're so common, the physics are well understood. The physics are universally applicable, at least while you're on planet Earth. And the data that's coming out of most batch tanks can be generalized. And that's a really important kind of assertion, that if we can generalize data, we can repeat an information model regardless of who the particular vendor or OEM or who the implementer of the batch tank is or where it sits in a system. So if we want to begin to get data out of one or more of these batch tanks, the Industry 3.0 way, the steps kind of look like this. If we haven't already got a PLC, we're going to get a PLC, and we're going to add the necessary I/O and instrumentation. Sometimes that's just running wires and screwing them into the I/O, or sometimes we're going to have to add additional instrumentation. For each instrument or set of data points from an instrument, we are going to build a tag list in our PLC. Those tags represent current values for the I/O. Then we're going to establish communication with our PLC using one of the hopefully modern protocols that are in the PLC, although we can't always assume they're modern. And then typically we're going to have that data sampled at a regular rate and stored in a historian. So we make a copy of a subset of the tags in the PLC, and we tell the historian that I want to store this a couple times a second or a couple times a minute. And we get that data flowing. That's usually then where we begin building an information system. So we acquire some information software that hopefully creates some value that we're interested in. And we use that software's setup tools to build the information model it requires to return the value it proposes. So that mapping exercise, where we take the tags from the PLC that have been copied to the historian and map those tags to the information model that the software package requires, is a set of steps that we cannot avoid because of where technology is in this space. So performing this information model mapping is kind of this necessary pain that we have to go through to get structured information out the other end. And then once we have structured information, then maybe we want to export that to some sort of tool or surface where we can begin exploring it and determining what decisions we want to make based on that information. And so I warned you earlier that I wanted to spend a couple minutes on this mapping exercise. So even though it doesn't make for a great demo, what I'm going to do is play a couple minutes of the setup experience for one common piece of software in this space. And I'm going to be kind to you. I'm going to play it at double speed. And the video itself is only a couple of points of data in the information model that the software requires. I've done my best to block out any company names or product names because I'm not picking on this particular piece of software. This experience is common to all information software in this industry. I helped build some of it, and it's just what we had to go through. So as we watch this video, let's not pick on this software. Let's just kind of be aware of what it looks like to map an OT system to an information tool so that we can get some value. All right, so we start by looking at our operation. It's already been partially modeled, so we know what some of the units are and where they sit in some kind of topological model. And in order to get to the value that this software provides, overall equipment efficiency, we need to know when a particular piece of equipment is running. So the first thing we're going to do is we're going to define running, and then we're going to choose a tag in a PLC that represents, hopefully, that can be used to indicate if the machine is running. And we're going to determine whether we should measure it when the bit is high or when the bit is low. Next, we need to repeat that exercise for the faulted state. So again, we're going to look for a tag in the PLC that hopefully flips from a low value to a high value when the machine is faulted. This is for a single machine, and we're going to have to repeat this process for every machine in our line that we want to measure this against. We're also going to model a specific kind of fault, so a problem with oil levels. And again, we need a tag in a PLC that hopefully indicates some measurement of oil level. And we're going to monitor that bit for a change. And we're going to use that to infer some sort of indicator of equipment performance. If we can reliably get to that, then we have an information model that tells us how effective this particular piece of equipment is. And maybe we can begin to plan some decisions around that. For each process unit, line, part of a factory, site, we're going to need to repeat this exercise, performing this mapping, and we'll probably go more detailed with the mapping for the different kinds of problems that we want to identify. So this is the reality of where we're at today, is we have to map the OT layer to an information layer. And this is where these hidden costs lie. If I need to add I/O or instrumentation, then I'm probably looking at some downtime while I make electrical changes to the PLC. I'm looking at a couple of days of this mapping exercise, depending on how many units I want to tackle and how many different problems I want to be able to pre-model, to pre-identify and map to. If I don't have tags that can help me identify the problems that I'm pre-modeling, I'm going to have to go get those tags, either pull them into the historian if they already exist in the PLC, or if they don't exist in the PLC, update the control program to adapt to new instrumentation or new calculations that happen in the PLC so that I can pull that through to the information system. And then I can actually start my kind of information journey. What am I going to do with this? And I need to repeat this pane for each unit that I want this value against. So if we want to make this smarter, if we want to leapfrog from Industry 3.0 to Industry 4.0, let's set ourselves some goals. We want to make this unit smart. So we would like to start with low-cost instrumentation. It'd be great to avoid a dependency on the PLC to start. That doesn't mean there isn't a place for the PLC. In fact, we'll probably end up there as we mature in this journey. But taking down an existing PLC or introducing a new one carries a lot of risks and a lot of cost. So it would be great if we could start instrumenting and gathering data without kind of touching the control layer at the start of our journey. It would be great as well if we could use low cost and low management information infrastructure. So each of those servers carries kind of this lifetime cost that can be daunting. If we can skip that and use low cost information infrastructure, this whole process can be a lot smarter. We'd like to simplify the connectivity. We would like to skip that modeling stage. As much as possible, it would be great not to have to remap tags to an information model over and over again. We would like our value to be app-based. So on my phone, I go to the App Store, there's an app I want to try, I install the app, and if I like it, maybe I'll pay them for it, and if I don't like it, I'm going to uninstall it, and the entire infrastructure for that app is removed from my phone. This app-based approach lets us try things in a low-risk way, and it's a lot different than deploying an application server in my infrastructure, which then becomes a sunk cost that if I have to rip it out, it's going to be painful. And finally, I would like my smart solution to be open and non-proprietary. That doesn't mean there isn't commercial software involved, but that commercial software doesn't have a particular vendor ecosystem lock. It doesn't require me to replace layers of my stack with particular vendors' hardware or middleware. At any time, I'd like to be able to try out a different vendor and know that the layers that I've deployed are open and interoperable. So that's what we're going to try to show you in a demo today. And before I switch over to the demo, I'd like to just tee a couple things up to talk about what we're going to be looking at. The first is a piece of gateway software that we have running on a Raspberry Pi. We wrote the gateway software in Python. It's open source and it's available on our GitHub. And the function of the gateway software is to replace much of that information infrastructure. This is a low-cost device doing a very simple job of connecting to an OT data source and securely transmitting data to the Smart Manufacturing Innovation Platform. So you're going to see the gateway running on a Raspberry Pi. We have a version of this that runs on a PLC so that as we kind of mature in our journey, we can move off of kind of consumer hardware to more industrialized hardware as we go forward. But this is a great starting place because it's low cost and low risk. The next piece you're going to see, because I don't have room in my home office for a full batch system, is a simulator speaking MQTT, pretending to be a batch system. So we've built some process units that emit data that look like a series of batch tanks that work together, and they transmit their data with MQTT. So I'm going to run that on the Raspberry Pi as well, because I don't have room in here for a bunch of tanks. The data is going to end up in the Smart Manufacturing Innovation Platform. It's transmitted in a secure fashion. So the channel that it travels over is encrypted, and that encrypted pipe has a certificate on either end to ensure the authenticity of both the sender and the receiver of the data. And then finally, you're going to see an app that we put together just for illustrative purposes using HTML5 technologies and our open API that uses GraphQL. GraphQL is an open language that we can use to explore type-safe data, structured data that's stored in a graph. So it's well suited to the Smart Manufacturing Innovation Platform. So those are some of the pieces we're going to look at. And let's walk through how we can make a process unit like a batch tank smart in this kind of new Industry 4.0 way.
First, I'm going to start up my gateway. This is the main on-prem information infrastructure, and it's running on a Raspberry Pi. It establishes a secure connection to my Smart Manufacturing Innovation Platform from my operation layer. While that's getting connected, let's go to the platform itself and see what we have. If you look here, there's a pumping station, and it looks pretty empty right now. It's going to represent my batch system, but there's no equipment in it. So let's change that. Let's go back, and we're going to start small and simulate just one tank and connect to it via some low-cost sensors. All combined, these sensors cost less than $100, and we can use them to instrument a batch tank and then send data to an MQTT broker, which the gateway will connect to, and then send the data to our platform. So let's get that started. If I go to my MQTT broker, I'll be able to connect to it and actually see the data coming in from the on-prem infrastructure. So let's connect. One of the really cool things about MQTT is it's easy to monitor the data right on-prem so we can see what's going on. So within MQTT Explorer, I'm able to monitor my tank as it is filling and emptying. The gateway is going to use the same data source, so it's going to be a true reflection of what's going on, both on the on-prem infrastructure and within the platform. Here's the trend of the tank filling and emptying repeatedly. Since the gateway is running, it should have created a new instance of an equipment tank in the platform. So let's navigate back to the Smart Manufacturing Innovation Platform and see what's happened. You'll notice now under pumping station, I have tank 1. This has happened because the gateway automatically detected a new tank existing on the MQTT server and created an equipment instance of it in the platform. Now we can actually go and trend the data, and we'll see the same data that we saw on the MQTT broker. Let's look at the live data. Let's auto scale to make it easier to look at. And here we have it. Although the two trend tools interpolate slightly differently, they're still illustrating the same data. We've got a nice fill and empty loop happening here. But no one had to do any modeling. The gateway just found the right profile to use and automatically set up the information model for us. We know that data is flowing, but we'd like to know if there are any apps that might work against this data, knowing that we have a pretty common process unit. So for the next part of our demo, we're going to give you a sneak peek into the Smart Manufacturing Marketplace. It's currently under active development, but we have a prototype here to show you. So if I navigate over here to the Smart Manufacturing Marketplace, you'll see a UI design that's exploring what the homepage might look like for the Smart Manufacturing Marketplace. Since I'm interested in asset performance, I'm going to see what apps might be available for me to choose from. So I'll search. And here we go. So right away, I see we have a Smart Flow Monitoring app. And I'm going to click on it and see what it might be able to do for me. So this looks like it's an app that monitors the flow of tanks in a batch system. Looks like it might fit the bill. And because it's available within the marketplace, there's no infrastructure costs associated with trying it out. I can just go ahead and add it to the Smart Manufacturing platform and see if it meets my needs. Now, at this point, some work still needs to be done on the marketplace side to get the app set up, but We're working on building out those capabilities within the marketplace. In the meantime, I'm going to switch back to my computer and I'm going to try to run the app from there. So right here, I'm going to start up my app. And then I will switch over to the web UI to connect to it. Once the app is started up, it's going to connect directly to my platform instance, and it's going to start looking for types of equipment that it knows how to analyze. In this case, we picked it because it was going to be able to match with my tanks and batch process. So I'll log into the app. And right away, it brings me to the tank overview page. Sure enough, the app has found a batch tank and it has automatically connected to it. It already knows the information model of the tank because the app was built against the tank profile. It doesn't need to ask me anything about tags or topics. It just immediately starts visualizing the data from my first tank because it's able to connect to the platform, and that platform has access to the data coming in from my gateway. Let's pause for a second to review what we've accomplished. First, we simulated the instrumentation of a batch tank using low-cost sensors. Then we connected those sensors to our gateway using an MQTT broker as our on-prem data source. The gateway then identified a profile to use and started to securely transmit the structured data to the platform. The platform then automatically created an instance object of the known tank profile and set up historical data storage. It provided a web UI to review our data to make sure that it was actually coming in accurately and made the data available in an open GraphQL API. Then we moved to the marketplace and we found an app that worked against that batch tank profile. We started it up and immediately saw the data being used. That's where we are now. We're in that app visualizing the data. Now that's a lot of progress from the Industry 3.0 way, but admittedly, it's still a pretty simple demo. So let's ramp up the complexity. We're going to now simulate four more tanks. We'll have 5 total tanks, and these tanks are going to actually have a relationship with one another. When one empties, the material is going to flow from one tank to the other. Let's run our multi-tank simulation. And what this should do is create 4 more tanks, and we'll be able to then visualize the relationship between all of them. So if I go back to the Smart Manufacturing Innovation Platform and I refresh, once again, the gateway has identified and created new instances of our tank because they're all based off of the same tank profile. Now there are 5 tanks in my system, and still there was no manual step necessary on our end to create these tanks for us. But what about the app? Is that also scalable and repeatable? Of course it is. The app isn't bound to a particular set of tags or topics. The app itself is based on the profile. So if we reload, we then see that we have all 5 tanks visible here, and we see that they are flowing one into the other. The app was written against the batch tank profile, and it'll scale for as many batch tanks that it finds on the platform. It's 100% repeatable and can be applied to anywhere the profile is found. Now, Jonathan, back to you.
Thanks, Olivia. So let's just recap what it took to get here. We started with an instance of the platform running in the cloud. We added some low-cost instrumentation and a gateway in the form of the Raspberry Pi. And then we found a profile-aware app that we could test out against our needs in the SM marketplace. And that was it. That's what it took to get from the OT layer to an information tool running against the platform. So let's check in on how we did against our goals. We wanted low-cost instrumentation, and we didn't want a PLC dependency to start with. So
we got a $50 Raspberry Pi, some $20 sensors, and we can always move up to the PLC as our needs expand. We wanted low cost, low management, highly secure IT infrastructure. Well, the core of this solution is always up-to-date software as a service running in a Microsoft Azure data center. Everything between the Raspberry Pi and the platform is secured and encrypted with certificates on either end to ensure authenticity. We wanted simplified connectivity. MQTT is about as easy as it gets. We won't always have equipment that speaks MQTT, but the gateway is extensible to support a wide variety of protocols. We wanted automatic information modeling. We got that through the profile. We wanted app-based information analysis. We found an app in the marketplace. And we wanted an open, non-proprietary approach. And everything about this stack is either open source or open specification. So you're not locked into any particular vendor. So where do these pieces fit in kind of this picture of the platform that we've been working on? Well, about where you'd think. The tank or the tank simulator and the sensor represent our OT network. The Raspberry Pi functions as our SM Edge connector. It's our gateway. The SM Marketplace is the SM Marketplace. It's in development. And the app is an example app that you could find in the SM Marketplace. It's an actual app. So everything is kind of where it needs to be, although we're developing it all. But there are some pieces of this diagram that we haven't highlighted, like the profiles. So I'd like to spend a couple minutes talking about our progress there, because I think by now everybody is kind of understanding the importance of SM profiles. So where do they come from? Well, they're coming from project teams. All our most recent projects are required to produce a profile as part of that project. They come from working groups and from standards bodies. So the OPC Foundation has created a mechanism for companion specifications so these working groups can produce open specs and are required to produce a node set. A node set is an OPC UA information model that is directly analogous to and compatible with an SM profile. So some of these profiles are coming from deep experts and working groups. But we need full industry participation. So if you have expertise in a type of equipment or a process, you need tools to create the profile, or you need a place to go to find profiles that have already been created. So CESMII's been investing heavily in both of those things. The first demo I'd like to show is the SM Profile Designer that we've been working on in partnership with some CESMII members and industry experts. And the other part that I can show a light version of is something called the Cloud Library. The Cloud Library is a joint working group between CESMII and the OPC Foundation, as well as a number of industry members who are participating in its creation. It is an open specification and open implementation of a common repository for OPC UA information models, in CESMII terms, SM profiles. So we've been working on that specification together for about 1.5 years, and I'm excited to be able to show an early version of the prototype implementation of that technology as well. So let's switch over and do some more demos. All right, I'm going to start here in the CESMII Profile Designer, and you can see that I have no profiles yet. I'm almost never going to have to start from scratch. I'm always going to be extending or deriving profiles that somebody else has built. So I can see here that I get to inherit from the OPC UA base namespace or base profile, as well as the DI profile. But I want to build a custom robot. So I'm going to import some additional profiles that somebody else has built. The first is the robotics information model, which comes from the VDMA and has been published as a node set. And then the second, a colleague has made for me. He's gotten started on our human robot. And these are both pre-canned profiles that I would like to extend or customize for my use case. So I'm going to import them both. And this is going to take a couple minutes. So for the sake of the demo, we'll speed through part of this. All right, so everything's been imported. the base namespace or profile, robotics, is here as a reference type. But if I look at my profiles, I'm going to see the human robot that my colleague and I have been working on. If I view the type definitions that are a part of that profile, I can see that there's an eye and that there's a mouth that has been defined. So I'm going to continue work on the mouth here. All right, so this is the robot's mouth, and I'd like to add some attributes to it. You can see that a number of attributes have been inherited from the profiles that I derived from, as well as this one in darker has been created by my coworker. I'm going to add another string type. And in OPC UA terms, this is a property. And I'm going to call this the robot voice. It's a property of the robot's mouth. And I'll add that to the list of attributes. So now the robot has a voice. So let's save that. And we'll see that the type has been saved. Now, if we go to the type library, we can take another path to adding things. If we want to add a whole new component to our robot, we're going to start with the component type. So I'll search for that. And you can see component type comes from the DI information model. And I want to extend the component type. So this is a concept that's been created, but I need to build some custom characteristics for it. So it's of type component type, but it is a robot arm. I'm going to give that at least one attribute as well. I imagine the robot arm moves, so it needs an axis to move on. Fortunately, axis information is something that's also defined for me in one of these base profiles. It's also going to be a property. Call it the arm axis. The axis robot arm rotates on. And we will add that property to the robot arm. Now, when I go to save this, I'm going to get prompted what I want to save it on. Since I started this component by deriving from component type, I need to specify where this extension belongs. It belongs in my human robot. So I'm going to save that there. And this has extended the type and added it to my human robot profile. If I view the type definitions for that, I can see that I have my new robot arm. Now that my robot is built, I want to share this profile with others. There's a couple different use cases for that. Perhaps I want to use this as a starting place for formal companion specification. So it's an input for a working group. Perhaps this is done and I want to share this with the world. So this is something that I'm going to submit to the cloud library to have available on the SM Marketplace. Maybe this is something I want to import into my SMIP instance. So in the very near future, we'll be able to connect these directly and import from here into the type definitions in the SMIP. For now, though, I'm not sure what I want to do with it. All I know is that I need the output of my work. So I'm going to download this profile. And what's going to come back from the profile designer is a valid OPC UA node set. And you can see here that I can save that node set and use it the way I would use any other OPC UA information model node set. As I mentioned, one of the ways you might want to use this is to submit it to the cloud library. So this next part of the demo requires a little imagination. The cloud library prototype is in early days. The working group formally finished the specification a couple months ago, and now the teams have been collaborating on this open source prototype. So this is going to be a test page. We don't have a UI for this. Test page doesn't make for a very glamorous demo, but if you've done any software development, you know this is a great place to start. So let's go to the test page for the cloud library. And you can see here the methods that the cloud library supports. And an obvious important one is going to be the find method. So if we take a look here, here's the find method and we can try it out. So let's say I wanted to find who had worked on robots before. I'm going to add that as a search string. I'm going to execute my search. And I can see here in the results that it's pointing to a node set XML. So if I copy that and open a new browser tab, I can see here this node set XML. That's the very same node set that I started with in my profile designer. So you can imagine a near future integration between these two, where I import and search from here to the cloud library, and I can publish back from the same experience. This sort of ties all the pieces together and hopefully gives everyone the tools they need to make sure that they're not reinventing the wheel every time they need to define an information model. So if we go back to this diagram and see where these things fit, the profile designer is a tool for designing profiles, but more than that, it's a way to help users find profiles and customize them to their needs. The anti-pattern is creating from scratch. The pattern that we want to drive towards is derive or extend published profiles with only what's unique to your application. In order to facilitate that, we're going to need a tight integration with a repository of profiles. And that's this CloudLib effort with the OPC Foundation and about a dozen other industry participants who all are aligned with this goal of having a common place to look for published profiles so you don't have to reinvent the wheel. That's the profile side of this diagram. The other side of the diagram we haven't touched on yet. And I'm excited to invite Dominic from Symphony AI to show how their AI and their workflow engine can connect to the demo we've built and automate decision-making and action-taking based on the data that we find coming out of our operation.
Thanks, Jonathan. Glad to be here. This demonstration is based off of a physical system of a series of tanks. In this image here, we're describing that physical system. In the first tank, at the start of the process, it will fill up from empty to some maximum volume. Once that max volume is reached, the contents of tank 1 will transfer to tank 2. Tank 2 will fill up to its maximum volume and then transfer to tank 3. And this will repeat until it reaches tank 5. When tank 5 reaches its maximum volume, it will begin to drain. Once tank 5 empties, this process repeats itself. So let's start with taking a look at the raw data. On the CESMII platform here, we're going to show that raw data in a time series plot. We will display the volume from each tank. And let's set that to live and auto scale. So we're looking at the last 5 minutes of the raw data from the tanks. These are the volumes across each tank. Excuse me. The volume is shown on the y-axis here, and time is shown on the x. So we see a pretty consistent cycle of changes in volume. And what I'll do now is I will initiate a leak. And what we'll expect to happen is that our system will detect that leak. It will alert on that leak, guide our root cause analysis, and then ultimately issue a work order as to how to fix that leak. So now watching the raw data here, we see that our red line, this represents the volume of tank 1, and this purple line is representing the volume of tank 2. In the past cycle, the prior cycle, the tank 2 reached the max volume of 20, which was also equal to the max volume of 20 on tank 1. So all the contents from tank 1 transferred to tank 2. However, we see in this current cycle that there was a significant amount of volume lost in that transfer. So that's where our leak is occurring. Now, we'll take a look at our alert here. I received an alert in my email, and we see the alert, the ID number, and then the asset that alert happened on. And so this alert was sent to me over email. This could be sent over a number of means. Could have been a text message, a phone call. We could be pushing, flipping a switch on a dashboard, pushing to really any of the systems that make sense for the factory. And that's really where the flexibility of this platform excels. Now, we've been talking a bit here, so I didn't respond to the alert in time, so now I've actually received an escalated alert. So this really makes sense when it's a mission critical issue that came up, such as what we have here as a leak. And in practice, we'd likely see this escalation sent to, likely my supervisor, someone who's on site who can provide that priority response to this. So now let's get into the workflow. So I'm going to go into our task list here, and I'm going to open up the task that's pending. So confirm leak on ground is the task here. Investigate detected leak on tank 2. So we're given our first instruction here, is there evidence of leaking fluid on tank 2? I'm going to look at tank 2. I see some liquid on the ground, so I'm going to select yes. I confirm that there's a leak. And now we're put through a set of questions that we've configured to determine and record where that leak is coming from. So these are standardized instructions that help guide our root cause analysis. Is the inlet connection leaking? No, it's not. Move on. Is the outlet connection leaking? I'll take a look at the outlet, and I do actually see the leak coming from there, so I'm going to select yes. And upon further look, I noticed that the gasket is actually broken, so I'm going to make a note of that. And this note that I'm putting in here is going to be captured in our work order that we're going to submit against this alert that's been risen about the leak. So let's put that. We're going to submit that. And upon submission of this, our solution here is generating work order. That work order for the case's demo is going to be through an email. However, in a real world use case, this could likely be pushing to a CMMS. So now we see our work order request, an ID number, the priority of it, what's the location, the asset, who requested it, and then a description. Going through the workflow that we set up, we confirmed that the leak was from the outlet connection, so we see that under the description. And then the additional information that we submitted was that there was a broken gasket, and we see that here below. So really quickly and easily, we're able to incorporate information from the user through this user interface here. It could be on an HMI down on the factory floor. Now let's back up a couple steps here and let's show how this was implemented. Here's the Symphony AI Workflow Designer. And this is that graphical user interface that makes it really easy for the OT user, so your manufacturing engineer, your technician, to design and define these processes. So at the beginning here on the top left, we see the fault event detected. So that was the leak that occurred. And then as we move through here, we see a few different types of icons. And these blue icons enable the workflow to interact with external systems. So issuing alerts, issuing a work order. And then these purple icons are a way that the workflow can interact with the user through the HMI that we were just talking. So really quickly, we can see how this was built out just by drag and drop interface. And you could also see how this could be extended. So when we worked through here, we confirmed the leak on the ground. So we went down this pathway. We were asked about the inlet connection. And then we confirmed that the leak was at the outlet connection. However, there are other avenues that we could have taken based on our investigation of that tank. We could have reported a different issue. And then maybe a few weeks in the future, we discover that there is a new common failure mode. And this workflow could then be updated to incorporate that with easily just adding another one of these purple icons. And then finally, at the end here, we have the issue work order, which concludes the process of the monitoring the system, detecting an anomaly, alerting on the anomaly, supporting root cause investigation, and then finally issuing that work order to the CMMS so that the issue becomes addressed and fixed. This includes a demo. Thank you for listening. Back to you, Jonathan.
Thanks, Dominic. That was really cool. We covered a lot of ground today, so let's just do a recap of everything we've gone through. We saw some of the challenges we're facing today with Industry 3.0 technology and kind of the legacy of how we've evolved to this point. We got a glimpse of a way forward using open, low cost, and secure tech. We looked at an upcoming open source tool to derive and create standards-based information models or profiles, an upcoming repository for those profiles that is open and accessible to all. What we couldn't show is that CESMII is funding a number of projects that are just getting started to provide conversions from common proprietary template or profile formats to this new open format. And we saw AI and workflow leveraged to detect and respond to problems. There are some missing pieces here. Like I said, this was a glimpse of what we're working on. Part of the reason that this demo was so automatic was that there was a profile, but also because our simulated equipment implemented a special kind of profile called an interface profile that allowed it to identify itself. This made it easy to match the incoming data to a profile in the library and automatically create the instance object. There are a number of efforts underway to accomplish this in the industry. They're not currently harmonized. And so that leaves us in a situation where we've got kind of two choices of how to go forward. The hard way is what I call heuristic discovery, which means I'm going to look at the full set of data and the patterns in that data and try to match it against the patterns in the information models published in the cloud library, and hopefully find matches or close matches, and then maybe get a user to confirm them. This is better than a tag picker, but it's still not fully automatic. To get the fully automatic solution that we've shown, we need an embedded identification profile, an interface that everybody can agree to, or at least agree to some common data members for, that allows us to identify the object that's coming in. That harmonization effort is not a lightweight one. It's not one CESMII can do or dictate. We really need to work together across industry groups. And I'm excited to say that that is happening. If you missed our information model harmonization panel, please go check it out on demand. It's really exciting. These are some of the top minds in this space. Some of them have never met in person, and they have very different backgrounds, but they're saying the same thing, is that we need to move towards harmonization. And that's actually happening. If you're ready to explore some of this stuff, if you're ready to participate, whether it's in building profiles or building apps or lending your voice to harmonization, but you want more information, we have a couple sessions coming up. Two of them are from my teammates. You met Olivia earlier for the demo that she did. She'll also be doing a getting started session for users and administrators. And then in that same block of time, but in a separate session that happens later in the time slot, Dave Wickman, who's on my team, will be doing a developer's guide to the platform, specifically for OT and IT engineers. So if you're both of those personas, you're welcome to attend both. If only one of those applies to you, come for the part that applies to you. And if you're looking for more resources online, we have over 30 hours of recorded user training material. We have code samples in 4 different programming languages. We would welcome pull requests for more if there's a language you're passionate about that's missing. We have documentation, and we are active on Discord. So me and my team can be reached there if you need help getting started. Everything we talked about today was fairly technical. This was a technical session. If that's not your background, or maybe you're a small or medium manufacturer who doesn't have a software development team on staff, that's okay. Smart manufacturing is still for you. We wanted to end this session with a video we put together that hopefully addresses some of the concerns or questions you might have about the feasibility of getting started with smart manufacturing. We had a lot of fun making this. We hope you enjoy it.